All right, so where we left off was about balanced forces. Now, if we have a balanced force, we said the net force is equal to zero. We say Newton's first law is an object in motion needs to stay in motion, or an object at rest needs to stay at rest unless acted upon by an outside force. The net force is zero, so there is no outside force. So therefore our acceleration is zero, and we're back to the same scenario. The only motion that can happen with balanced forces is constant velocity, either no motion at all where it's at rest, or constant velocity where it's in motion and it will continue in that motion, because all of the forces are balanced. So that is the only option that we really have. Describe the motion of a stationary system with balanced forces. So once again, stationary balanced forces, it stays in place. Describe balanced forces acting on a continually in blah. Describe the balanced forces acting uh, uh, commonly encountered moving objects, such as cars moving at a constant speed or a person walking upright. So, in that case, for there to be balanced forces, there needs to be equal forces. Now, if you're moving in a car, you have the force of gravity, Fg, going down, but you're going to have a complementary force, an equal and opposite force. This is Newton's third law of a normal force. This normal force is pointing up. You're going to have some drag forces, some forces of friction. This comes both from the wind that is pushing against your car and the rolling friction of the wheels. So this is going to be a force friction. It's going to hold us back, FF, force friction. It is going to try to hold us back. For us to stay at a constant velocity, we have to apply some kind of forward force. So this is a force applied. This force applied is what we are pushing on the accelerometer, the gas pedal in the car. That is what's creating that applied force that needs to be equal to the force of friction. If we did not have that, we would not have balanced forces, and therefore this is not really applicable. Same idea with you. You have mass, that means that you have a force of gravity. You're touching the floor, that means you have a normal force. There is going to be a force of friction. The air is pushing against you. This is a very slight amount, but you can apply an equal amount of force of you moving forward by pushing against the ground. So the ground is applying a friction to you. You are applying a force to it. That means that you have balanced forces. So therefore the net force is zero, the acceleration is zero. Identify and describe forces everywhere around you. So we are sitting in a chair. This chair is preventing us from falling down to the ground. So same scenario. Force of gravity is pulling you down, but you're sitting on the chair, so there is a normal force pointing up. There would not be any force of friction because you're not really moving anywhere and you don't have to apply a force. So in this case, we have the force normal, and you have the force of friction or force of gravity going down. So that could be you. Something else could be you push the wall pushes you. So you're applying a force to the wall. The wall pushes you back with an equal and opposite force. This would be the force of the wall on you. So that would be a normal force because you're touching the surface. So there's a normal force that is equal and opposite to the applied force that you're applying to the wall. Those are some examples. I'm sure that if you thought about it, you could make up even more. Draw a force diagram of an object using vectors. All of these are force diagrams, and we've used vectors. You have plenty of examples, you have plenty of experience drawing force diagrams. I trust that you will be excellent at this. I can measure forces using a spring scale and force sensors. You remember when we did the forces at an angle, we had a spring scale that measured in Newton. If you'd like me to demonstrate this before we take the final, I'd be happy to. But basically, you attach two things to the spring scale and just read what force it says. It's super simple. Find the net force of an object. All right. So, if we have a force here that is 10 newtons. Force in this direction, that is 5 newtons. A force in this direction, that is, we'll make this one 2 newtons. A force in this direction, that is 5 newtons. Of course, remember that these vectors are not exactly drawn to scale. It would be much better if they were, but they are not. I've tried to make it good, given the limitations that we have. So, net force, F net is always the right forces minus the left forces, and the up forces minus the down forces. So our right forces in this case is 10 newtons. So we have 10 newtons minus our left forces. Our left forces is 5 newtons. That equals to be 5 newtons. Our up forces in this case is 5 newtons. Our down forces in this case is 2 newtons, which gives us a total of 3 newtons up. So this would be 5 newtons to the right, this would be 3 newtons up. So that is our net force. Our net force is 5 newtons up, 3 newtons right. Or 5 newtons right, 3 newtons up. Just remember, it's right forces minus left forces, up forces minus down forces. That is the net force. That's how we calculate it. Describe how the net force of an object affects the object's acceleration. This is Newton's second law. Force is equal to mass times acceleration. You remember this one. So, how does the net force of an object affect its acceleration? If we assume that we have a constant mass, if we have a higher force, we have a higher acceleration. Let's see, does this make sense? If I push harder on something, then it's going to accelerate faster. Yeah, makes sense, right? All right. If I, however, have a smaller force, it's going to accelerate less. It's going to move, change its velocity less. Relate an object's mass to an object's acceleration when an unbalanced force is applied. All right, same idea. Force is equal to mass times acceleration. So, if our acceleration needs to stay constant, if our force needs to stay constant and we increase the mass, that means that the acceleration will go down. So basically the same as saying if we push equally hard, then a heavy thing, a thing with a lot of mass, is going to move less or change its velocity less than if it is the same force we're pushing to a mass that is smaller. So we're going to have a higher acceleration if it's a lower mass. We're going to have a lower acceleration if it's a higher mass, assuming that we are pushing with the same amount of force, so the force is constant. Use data about force, mass, and acceleration to support Newton's laws. So this is several labs that we have done in class, but we can definitely do the same thing. All you'd have to do is prove that it is heavier things needs more force to move them. We can use the spring scales to demonstrate this. I'd love to do that when I return to class with you before we do the final. Predict the efforts of several forces acting on an object. If you have a force acting on an object, then it is going to accelerate in that same direction. That's the best answer I can give right now to that one. I might have to think about that one a little more. Identify pairs of forces between two objects. This is Newton's third law. For every action, there is an equal and opposite reaction. So if I push the wall pushes me. If I kick the ball kicks me. Any time you are pulling, it is also pulling on you. Force always comes in pairs. If the Earth is pulling in on the moon is pulling in on the Earth. Find the magnitude and direction of the acting force when you know the magnitude and direction of the reacting force. So, if we have a force in this direction, we know the direction, we know the force, so let's say that the force is equal to 5 newtons. The reacting force is always equal. That means that it must necessarily also be 5 newtons. And opposite, so the direction is opposite of it. So it must necessarily be 5 newtons going in the opposite direction. It is equal and opposite. Forces are always comes in pair of equal and opposite pairs. This is Newton's third law. Provide examples of Newton's third law. For every action, there is an equal and opposite reactions from everyday life. I just went over several of these. So I kick the football kicks me. I push the wall pushes on me. If I open the door, then I am pulling on the door. Therefore, the door is pulling on me. There's always equal and opposite reactions. Just you sitting in the chair, you are pushing on the chair. Gravity is helping you push on the chair. There's equal and opposite forces. The chair is pushing on you. Um, how did we develop Newton's third law, and how did we explain how the development of Newton's third law is an example of how scientists build on previous knowledge and relies on experimental evidence. So Newton did a lot of these experiments himself, um, tried it out, but he also used several of the things that came before him. He's not the first person to notice all of these things, but he is one of the first to note them down. Aristotle had several ideas about motion. He was wrong, however, but he started out with some of these ideas. One of the things that Newton was mocked for was Aristotle could explain why do things fall, like they fall to the ground because they're made of earth and therefore wants to return to earth. Newton didn't have a very good explanation for why is these forces equal, why is this the way it is. He just did experiments and found out that that is what the data shows him. This is what the evidence is. Explain how to use measurements to explain how mass affects the gravitational force. So, mass, we're still dealing with Newton's second law, force is equal to mass times acceleration, but in the case of gravity, then the acceleration is something special. It is the acceleration due to gravity. So we have force is equal to mass times, and we give the acceleration a special name. We give it the letter G, G for gravity. And the acceleration due to gravity here on Earth is 9.8 meters per second squared, because we're talking about an acceleration. So this is G. Let me make that a little clearer. So this is G, the acceleration due to gravity. So if we increase the mass, that means that we also increase the force. So things with a greater mass have a greater force. Things may fall at the same rate, but they need more force because they have more inertia in order to fall at the same rate. Things with more mass does not have the same force. They have a bigger force because as you're multiplying by a constant number, you're going to get a number that is bigger if you multiply by a bigger number. Distinguish between mass and weight. Weight is your force due to gravity. So Fg, force due to gravity, is your weight. Your mass, however, your mass is how much stuff you're made of. If you go further and further away from Earth, even goes out into space, you're going to be weightless. That means that the force of gravity is basically neglectable. It becomes such a small number. However, you're not going to be massless. You're going to be made of the same stuff. So if you go to the moon, then the gravitational acceleration of the moon is going to be much less, which means that you're going to have a much smaller weight, so you'll weigh less on the moon. However, you're still made of the same stuff on the moon, so therefore you have the same mass on the moon. So mass, the amount of stuff you're made of. Weight, the amount of force that gravity is applying to you. We often confuse those two because one of the ways we often measure mass is simply by putting it on a scale and seeing how much the force of gravity weighs it down, because they are directly proportional to each other. However, mass and weight, most definitely not the same thing. Describe how the distance between objects affects the gravitational force. Now, we can use this one, but we also know the universal gravitational constant, so F capital G, is equal to the mass of object 1 times the mass of object 2 divided by the distance between them, so r squared times capital G. So the mass of the two objects, the distance between them, multiplied by the universal gravitational constant, that is going to be our force of gravity. Now, if we are going to increase the distance between them, then we're dividing by a bigger number, but not just a bigger number, because it's a bigger number squared. So if we make it twice as far between them, then this would be 2 times bigger. 2 squared, that means that it's 4. So we're dividing by 4 instead of 1. So by doubling the distance between the masses, you're going to have 1/4 of the gravitational constant. Now, if we were going to triple the distance between the two masses, then we have 3 times as much distance. 3 squared is 9. So we're dividing by 9. That means that we're going to have 1/9 of the force if we increase the distance between them. If we, however, were to reduce it, then we're going to be dividing by a fraction. So like if we say half the distance between them, then we're going to start with a 1, or start with a half. A half squared is 1/4. Dividing by a quarter, that's the same as multiplying by the reciprocal, or the same as multiplying by 4. So if you half the distance between them, you're going to multiply by 4. So 4 times as much force of gravity. Describe how, explain how evidence and inference are used to describe the fundamental forces in nature. Inference is our best educated guess. I know that there is light on this paper. I can't actually see where the light is coming from, but I infer that since I'm inside a building, it's probably not from the sun. It's probably from a lamp. I can't right now see this lamp, so this is an inference. I don't have any actual evidence, anything I can measure to tell that it is not the sun that is lighting up this piece of paper that we're looking at. This is a fairly good inference, but still an inference. I don't have any concrete evidence. It's not something I can measure, something I can take data on. Just a reasonable guess. We use those to create fundamental laws in nature all the time. Name some importance of gravitational forces in the space program. You, for instance, have gravity assist poles. So, if we have here a planet, then you know that the force of gravity is going to pull this in. So as the spaceship is traveling in here, it can come close to this and therefore being pulled in to this planet. They can use this being pulled in and then fire their boosters, and once they come out of it, they're going to have an increased force. They're going to have an increased amount of energy because they used the force of gravity of that planet to move it in. This is what's called a gravity assist on the space program. Also, we've discovered several interesting things happen in space with what we call microgravity, where the force of gravity is so small because we have a big enough distance between us and the Earth that microgravity seems to do something interesting to both bodies of humans and any other living things. These are often detrimental to our health. Often we found that it can lead to muscle loss, it can lead to several different diseases. we are used to having the force of gravity pull us down on a regular basis in our everyday lives, and that's not necessarily always the case. All right. So, up next we have charges. When we're talking about charges, we're talking about Coulomb's law. So let me remind you of Coulomb's law. Fe is equal to the charge of object 1, Q1, times the charge of object 2, divided by the distance between them squared, times a universal electric constant. We'll put it as K. This is Coulomb's law. The types of charges we can have are positive and negative. We can also technically have neutral, but it's kind of weird talking about neutral as a charge, as neutral is defined as the absence of charge. Positive is when you have removed some of the electrons from a substance. That means that it now has more protons than electrons, and therefore it has an overall positive charge. And negative means that it has too many electrons versus protons, so it has an excess of electrons. That gives it an overall negative charge. Just like magnets, you know that north and north repel each other. The same thing with charges. Negative and negative repel each other. Positive and positive repel each other. And neutral and positive doesn't do anything because it's neutral. Neutral and negative doesn't do anything because it's neutral. Neutral doesn't do anything. We might as well ignore it altogether. Negative and positive, however, is kind of like the north and south pole of a magnet. They will attract each other. So those are the type of charges and their effect on electric forces. So describe how the amount of charge affects the electric force. So if we have a higher charge, we're going to have a higher electric force. Bigger Q's means a bigger electric force. A higher numerator means a higher fraction, which means that our result is higher. The relationship of distance between the charges to the strength of the electric force. It's the inverse square law again. It's this R squared relationship again. So just like we talked about universal gravity, you have to remember to square it. So if you double the distance,